Hey everybody, thanks for coming today, even with the Clement rhetoric. This is the most people we've had since we started in last year. Today we have Chris Saunders, and he'll be talking to us about teaching garbage collectors. Thanks.
So just thanks everyone for coming out. This is kind of scary, but I'm going to be talking about the paper Teaching Garbage Collectors Without Implementing Compilers or Interpreters by Greg Coopher and that team. It's a very extensive list of people who worked on this project. So before we get started, we're just going to kind of go through the breakdown of how we're going to go through this. So we're just going to talk about the fundamentals of what it is that are in a computer that we need in order for us to kind of make sense of garbage collection. And then we're going to pose the question, what is garbage collection? Some of the obstacles that are involved in learning, which is covered in the paper they talk about, and then the tools and a demonstration. So the tools are the thing that Coopher and the team built to help overcome the obstacles that they mention. And then I'll just do a little bit of a reflection on the garbage collector that I built, some of the problems with it, and then we'll just have a few closing remarks about that and some things that are related to it that you might be interested in. So the fundamentals. I'm just going to cover a few things. A lot of this isn't, if you've been programming for a while, it really isn't new, but if you're new to computer science or this is your first time hearing about garbage collectors, we're just going to go over and we're going to kind of set a common language. So what is memory? So memory is where the data that our computers use to process stuff goes. So whenever I go to assign a value, it has to go somewhere, and that'll go in memory. Memory is, there's two types, which we will cover very soon, but these have different behaviors, and depending on which ones we're working with, it has certain implications. And then there's garbage. So whenever we're talking about memory, what is garbage? If you've ever written or worked in a language that isn't garbage collected, like C, if you have a pointer and you stop holding onto it, like your program finishes executing and you didn't clear that memory away, that's just garbage that's floating around and you can never get it back. And if you keep on calling these functions, you'll eventually end up consuming all of your system's memory and your program will crash. So one of the ways we can store information in our memory is using the stack. It's kind of like a Pez dispenser. So this is the visualization my CS prof used back whenever I was in university. So whenever you'll have a function, and in a statically compiled language like C, if I define at the top that I'm using an integer and an integer pointer and a structure, I know at compile time how much memory I need in order to do that, perform those operations. And so whenever I call that function, a bunch of stuff will get put in the stack, and then I can set the values and read them and all that kind of stuff. But that's only good if I know how much memory I will be using at compile time. And unfortunately, the world is a really, really messy place, and sometimes we have to work with data that we don't know what it'll be. So this is where the heap comes in, and this is where those memory leaks and where all this garbage comes into play. So I'll say I need to store something that I don't know how big it is until it's at runtime. So I'm going to store a pointer on the heap that will point to this, and I will allocate that memory whenever I need to, point over to it, and then whenever my function is done, I will relinquish that memory so that my other functions can use it again later. And as I said, if you don't release that memory, it just sits there until your program crashes or finishes execution, at which point it will be cleared up by the operating system. So allocation. This is the part of actually saying, hey computer, I want to get some memory. I have a few visualizations here that kind of show what happens. So on the bottom we have, I did the stack horizontally just because I don't know why. And then we have the heap on the top, and these wonderful lines are pointers into the heap of memory that we're pointing to. And that little arrow at the bottom right here pointing at C, this is this is our stack pointer. So anything to the left of that is memory that we still know about. And so we know that I don't know why I used colors. This one and this one, they're still being referenced to, so they're still alive, and I know it's all good. But the farthest one on the right, we don't know about it anymore. It's gone. And if we call another function, it's going to get overwritten by whatever our function needs to do to prepare itself. So that pointer will point to memory that we will never be able to get to, and we also have this little piece of memory over here that is unused. So if we're in a language that doesn't have garbage collection, this can be a real big problem. We call these functions a few times, and we are eventually out of memory, and we can't, our program will crash. So this is where the garbage collector comes in. So this is a program that runs underneath our programs that keeps track of what's going on, and it will be like, okay, cool, these things are still alive, but these things aren't, and it will relinquish them for us. So if we're using a language like Java or Ruby or Lisp, these are garbage collected languages. I don't have to worry about whenever I say new, that object will be I have to be like, oh, I'm done, now I have to clear it away, and I don't have to worry about all of that. The garbage collector will take care of that for me. This does come with its own implications, which we will cover relatively soon. But if we go back to that example, basically we have this mark phase that goes through and it scans through everything. So we use what's known as the roots, which we can get to via the stack. So we go through, oh, this thing's pointing to something, I'm gonna follow it, and I'm gonna mark that thing as valid, still in use memory. And then I'm gonna keep going, oh, this thing is still in use, mark that as still in use. And then anything that isn't in use, I go in and then clear it. So they're still kind of there, but you can't see them, which is great. So now we can use this memory again at a later point, and we don't have to worry about our programs crashing. That is under the assumption that our programs aren't really weird and just constantly allocating objects and holding onto those references. Like a normal, if you run a Rails request, you'll create all these objects, and then when the request is done, all those objects are just floating around in memory, and they are they'll get cleaned up by the garbage collector at some point in time. But this is great, but this is all theory. We can understand the theory really, really easily. A really simple mark and sweep collector is really easy to understand. But unfortunately, if you wanted to implement one, there's a bunch of obstacles that get in the way that can honestly be courses on their own. If in an academic context, or even just on your own, trying to learn how to, if I want to build a garbage collected language, I have to, there's all these prerequisites. So I have to know how parsers work. So I have to know I have to know the various kinds of parsers, the advantages of them. I have to learn how to use a parser generator and how to build up all of these tokens in order to just even consider getting started. And even still, just because I have all these tokens doesn't mean my program can run. Then I have to run that through a compiler or an interpreter before my program is even, before I can take my program that adds up a list and, runs. So there's, these two big obstacles that get in the way that are content, big subjects on their own. But if you just want to understand garbage collection and you're cool, I want to implement a mark and sweep garbage collector, I can't. Now we have languages that are garbage collected, but they're these are production systems. The Java virtual machine is garbage collected, but they're not really designed for me to go in and just drop in my own garbage collector. That'd be super awesome if I could just go in and build a really, really terrible mark and sweep garbage collector and be hey Java, use this one instead. Or go in and be hey Ruby, use this one. That'd be awesome. That'd be super cool because then I could write it in my own language, in Ruby or Java, something I'm comfortable with. Build my garbage collector and then have it do this. But these are systems that are super they're super tuned. There's been a lot going on in the Ruby virtual machine to get it to where it is today, and it's not it only has one garbage collector. You can't really swap them out. So we can go in and use toy languages, but toy languages don't like they work, but they don't cover everything. You could build one and build your garbage collector, but maybe the toy language isn't complete in the sense that you'll get all the edge cases that you would get in a normal programming language with a real garbage collector. So you build your toy garbage collector, it works, but you don't get to like expand out and try out all these other things that you can with a real language. So this is where the authors went in and they're like, let's try to like break this down. Like, let's get this wall out of the way so I can be like, hey, we're gonna build garbage collectors and that's all we're gonna do. We're not gonna worry about parsers. We're not gonna worry about anything else. We're just gonna focus on, say, building a mark and sweep collector. They built this like language on top of Racket. So Racket is a scheme. If anyone's done like second year university, you've probably worked with a scheme in some way. So it's a list. There's lots of parentheses. Parentheses are awesome. And they implemented it in two ways. So there's two things you need in order for your collector to be used. You need to build your garbage collector. This is done using the apply collector module or the language. And then you need a mutator, which is done by saying, my program uses the apply mutator language. So what's a mutator? A mutator is a thing that if we are a garbage collector and we look at it, these are things that come in and mutate state that I'm managing. So really, these are just programs. My program, this sum list, is going to be mutating the heap as it runs, and I need to keep track of that. And whenever I run into a problem, I need to either crash or do something so that I can really give more space back to. I need to free up more space so that other people, other programs, or other functions can use it. And then there's what is a collector? So a collector that's the thing we're going to be writing. That's the garbage collector, and it has a few responsibilities. That'll be implementing the allocation of the objects we want to work with. Whenever we can't allocate those objects, reacting appropriately, crashing, or running the mark and sweep or doing whatever. And in apply mutator, there's an interface we have to implement in order to be a valid collector for our mutators to work. So these are the only functions you need to implement publicly. These are going to get exported by your module that you write in Racket, and you'll include this in your mutator. You'll be like, I am using my really terrible garbage collector with 64 slots of memory. It'll the apply mutator thing will go in and do some stuff, and it will redirect all calls to your garbage collector instead of Racket's garbage collector. So it kind of gets in the middle, and they do this using they use a bunch of macros to do. They use a bunch of macros to expand out what your really simple Racket program is, so that it is always using your garbage collector. So init allocator, that's where we say we're initializing our heap. Go in, make sure the heap is in a consistent state before we get started. So if you're using a mark and sweep garbage collector, you could, and your free memory, your free slots are marked with the symbol free, you go in and go through all of your memory and add the free symbol to every slot. Then there's the dereference, read the value from the heap. So whenever I ask for something, I'm asking for the value of something at an address. And I will say, give me the value at address 7. My garbage collector goes in, looks at it, and it'll either be like, that's not a valid address, or here, oh, you asked for the value for a flat value, and oh, that is the value 7. That's terrible. Anyway, in my garbage collector, it's not like that. I have a really, really inefficient way of storing data. And then there's just our allocation. So allocating flat objects, allocating cons lists, getting the first value and the rest value of those cons cells, and setting them, and then we just have some predicates. So is this a cons cell, or is this a flat value? And yeah, so with this, we aren't working with we aren't working with full Racket. It's very much a small subset of Racket that still lets us write real programs, but we don't get the full functionality of Racket. We're basically working with two data types. You might know what they are from the interface back a slide ago. We have const cells, which are these things that point to a first and a rest, and these can point to whatever. In like a list, it would be first points to a value, which would be a flat value like 1 or boolean, like true or whatever, and then rest would point to another const cell. So if I have the list 1, 2, 3, it'd say 1, rest, and then 2, rest, 3, empty. So that's how that's how const cells work in Lisp. And then we have flat values, which includes a bunch of things. This is managed by Racket has this concept of contracts. So the authors were able to prevent you from cheating by only allowing you to work with certain types, which is booleans, predicates, or not predicates, procedures, numbers, symbols, and empty, I think. If you try to put anything else in, it gets really mad at you and crashes. And then the other thing they did is they built this heap visualizer. So I could ask what is exactly at location 14, and if I was working in a lower level, if I was building my garbage collector at a lower level, I might have to work with like heap dumps or other kinds of stuff. But instead, they've built this really cool visualizer. It's really ugly, but it's really cool. That lets you know what your heap looks like. So I could just run a program and see what my heap looks like at the end of the execution, but I can also go in and see what my heap looks like as I step through it with the debugger, and that's really, really neat to see. Like you can be like, I'm gonna break when the mark phase happens, and then you can watch the mark, like your mark and sweep actually happen and see it clear out the memory as it occurs. And it's pretty fun, and when you see it working, like after working on it really long, it's really nice. One thing this is what I found really, really nice is you can take a simple program and you can track its evolution on paper. So I was like really confused at the start. So I went in and I'm like, okay, cool, I'm going to sum a list. Here's my program, and I did like the evaluations to see what happens and how the heap is getting evolved. So I could understand what that visualizer was showing me and like understand how the program is getting executed and what's going on underneath. So that was really, really, really enlightening. And then as we can see here, so I have this cons list 3, and a cons list for my representation consists of some metadata. So all of my data that's stored consists of a little bit of metadata and some other, like the actual values. So for this is a cons list, or this is a cons cell whose head value, or whose first value points to the memory address 6, and whose tail value points to the memory address 8. And then I can follow that. Oh, this is a flat value, or a prim as I called it, and its value is 3. And then this one is a prim whose value is empty, which means that the list is terminated. As you can probably tell, I'm storing, like, if I store a flat value, it's like really inefficient because it's the metadata and then the value. So it comes at a bit of a cost, but it's really easy to understand. So the best way to get started with the collection tools in Racket, at least what I did, is I went to, like, the authors have like a garbage collector course, and you can go up there and they're like, okay, here's the garbage collector and here's an example garbage collector. It's a collector, it doesn't do any garbage sweeping or anything like that. So it'll work until you run out of memory, and then it'll crash. So it gets you halfway there. So I took that as my starting point and modified my functions such that I would be able to clear up memory as I need to. But we have to ask the question, what triggers a mark and sweep? So this is kind of important. When do we actually know that we're out of memory? And here's a Ruby example. So I will say I want to obtain memory of a certain amount. I try to allocate that amount, and I'll get a pointer back. If the pointer is nil, I know that I have no more memory available. So I'm going to run my mark and sweep, and then I'm going to try to allocate that memory again. If that memory fails to allocate again, I know that my heap is completely full, and in my case, I crash. Otherwise, I've set that pointer and I return it to the caller. So that is how, this is like mark and sweep. Like this is basically it. Well, this is how we run mark and sweep. And this is how mark and sweep is implemented. So I have like a little example of a mark and sweep. So on the left is our stack. This will contain what are known as the program roots. So from our stack, we're able to get into our heap, and then we will follow our heap through. So we start off assuming that our cells are all garbage. So that could be going in and setting all of the bits to 0. And then we have this middle state that is the unchecked references. So we know that they're alive, but we don't know if they have any children who also have to get checked. And then whenever they are done, we just set them as check cells. That'd be like marking them as 1 or whatever. And in this is the tricolor abstraction. So it's just a way of helping us visualize how we're going through and marking and sweeping. So if we were to start with our program, okay, we're out of memory, we need to run a mark and sweep. So we follow our program roots, and then we say, okay, those are the purple diamonds. So these are, we know that they're alive, but we don't know if they have any children yet. And then we go and we grab that one, we grab the first one off, and we check for its children, and mark those as, we add those to the list of things we have to check. And we mark that one as good. And then we just keep on going through and marking and following children. And then once we've gotten to the point that we've marked everything, we have no more references to follow. We know that everything else that isn't referenced is garbage, and then we just go in and we sweep it away and clear that up so we can use it at a later point. So this, I thought I heard someone say something. Okay. Okay, so this takes me to the demonstration part of this. So I went and built a Sweet. Okay, so I went and I built a garbage collector using, anyway, we'll roll with this. So using the tool that they built. Just up here, I learned how to export methods. The reason why I did this is they provide you with the ability to test. So you can go in and actually drive your development with tests, which is really nice because whenever you're first starting off, you have no clue what's going on. So what I wanted to do is, originally I had all of my tests in with my collector code, but every time I wanted to run a mutator, it was really slow and it was really noisy and all this other kind of stuff. So I went and I just did this provide. So I provide all these functions so that my tests can go in and access them. Just let me look here. I went and took a bunch of notes because I was afraid I'd mess it up. So I guess we'll start off by looking at where we initialize our garbage collector. So in my case, what I do is I represent all of my free cells as little pieces, like they're little slots, and I say they're free. So I add a free symbol to them. And because I don't have to mark anything, I just build up a list. I use build list a lot. It's probably not the best, but it was really easy to understand. So I just set my memory to a list containing every address, and then I tell my sweeper to go in and just sweep it all. So set every cell to free. And I guess we can go into the sweep function since that's next. It's right there. So sweep takes in a list of addresses. Unless the addresses are empty, set the first entry or set the first item off that list as free, and then just sweep the rest of the list. So keep on going until the list is empty, and it returns addresses. Hold on. Or it returns nothing. it possibly returns nothing. That's cool. I thought it might have returned something, but that might not be the case. So let's look into allocation next. So I did this really stupid abstraction, I don't know why. Yes. I did it because you can't, these functions are protected with, they're protected with contracts. So whenever you're trying to test things, if you're like, I want to allocate, it might be more of a problem for the consoles, but you're like, I want to allocate these two addresses, and it's like, those aren't addresses, you're not allowed to do that. So I built these functions that basically just wrap it, so I could just pass in addresses and be like, oh, set these two create a console or a flat value with these addresses. So in here, I have this find space for function, which I will explain later, because it's really, I have like a full page just explaining this function, because it's way too complicated. And then I just find the space, so I say, find the space for a primary value, and this lambda I got from looking at another garbage collector. So whenever you're working with whenever you call the get root set function, it doesn't just give you the addresses, it gives you these roots, and you have to get the root value from the roots, which will actually give you back the memory address. So I had everything working, and then I'd go to run it for real, and the garbage collector would kick in, and then it'd just like crap. Like it'd be like, oh, you can't do that, and I was really confused why. So I went and looked at a good garbage collector, and saw that they were doing this, and I'm like, oh, okay. So I'm just providing a lambda function, and if I'm passing in, if that flat value is a procedure, I know that that procedure might also point to other things, so I have to include its roots as well. And then I append those roots to the root set. Otherwise, I just return the root set because it's just a flat value. And then I allocate my flat pointer, or allocate my flat value with the pointer and the value. Yes?
So, what is a procedure in this context? Is it like a function?
It's yeah, so the question is, what is a procedure? And the answer is, it's a function, it's a lambda, or whatever.
So the roots, you mentioned like, okay, if it's a procedure, then you need to also look at its roots. Are functions roots like the stuff that it allocates on the heap in the body of the function, or is it the roots on the stack that are?
No, because they did a really sneaky thing. So you don't actually end up allocating a lot of stuff on the stack. They kind of push everything onto the heap. So you'll be writing a lot of functions, and everything just gets allocated onto the heap, so you don't have to worry about it. They actually, I failed to mention that, but they removed that part of going through the stack and figuring out what your function roots are. They maintain that for you.
So all the function arguments and everything are just like everything is a pointer to the heap.
Yeah. So and this is just because the procedure will point to stuff, but that won't be in our root set. So we have to append those to our.
Right.
We have to append those to that root set so that we get all the memory that's available. Otherwise, we can miss out on things. Depending on the implementation, or we would end up deleting things that we're not supposed to. I think I just like scorch the earth, so I would just delete stuff with like, I just go in and burn everything. So it's a pretty big deal. And yeah, so this just goes in, and then this is the heap. This is one of the functions that they provide. So this is, I'm setting the heap, I'm setting the address at pointer to prim, the symbol prim, and then I'm setting the pointer +1 to the value. And that's how I get those like prim values for my flat values. And then we have our consoles. These ones are where, like, this is where the testing became a bit of a problem. So you can't just say create a console with address 7 and 8, because those aren't heap references. So I got around that, not on purpose. Like, this was like, I did this for some reason, I don't know why, but it ended up making testing really easy, which is pretty cool. So we allocate our columns with a first and a rest. We once again try to find space for that. I have to pass in a lambda function of the get root set. You can't just pass in the function get root set, I don't know why. And then when we get the pointer, we go through and set those various things to those values, and then return the pointer. And yeah, this is another thing, is our function calls return the address of where the thing has been stored. these are really like, they're just checking a bunch of stuff. They're pretty boring, so I'm not gonna go over those in too much detail. Free memory is this is what we go through to actually find all of the memory that is available for us to use. And this is just by, we build up all of the available memory addresses and then do a filter map over it to get all the things that are free. If they're free, we return the address. If they aren't free, we return nil or something, and it gets removed from the list of free. Like, it doesn't get included in that list of available memory. And then we have find space for and slot of size. So this is why they're like, so slot of size is, it's a full page of stuff. So find space for is, this is, so if we go back to, I'm just gonna, new navigator. It's basically doing this. So we try to find the address depending on what type it is. We try to find a slot of size. That size based on a function called a free memory. And then we just call that, we set it to available addresses. If the available address, so I return a list of addresses. So if I requested slot, like space of 2, it would give me like 7 and 8. I don't end up using it, but it was really nice for testing. If it's empty, we mark based on that. We provide a get roots function, which was that lambda stuff I was showing earlier. We mark based on those roots, and then we sweep based on the results from the mark function. And then we check for available addresses again. If it's empty, we throw an out of memory exception. Otherwise, we return the new available addresses. And if, in the case that we didn't get it, we did get something back, we just return the available addresses. So this is where the magic happens. If the memory space is empty, we return an empty list, and that's it. Otherwise, we grab the first item off that available memory. This is our prospect. We make sure that the rest of the memory isn't empty, and we make sure that our neighbor is our address plus 1. So we take a look at the next piece of memory, and if its value is equal to our memory plus 1, we know that it's a consecutive piece of memory. This is more important for grabbing the memory of that size. If our size is 1, we return that one item as a list. Otherwise, we have this, we make sure that it has more memory, and that, if it has more and the neighbor isn't bigger than 1, we just go through the rest of the memory to keep looking. Otherwise, if it is, we go through and we just make sure that we can build up a list of the number of required elements. Yes?
So does this mean that you could end up in a spot where you say that you don't have any more memory just because of fragmentation?
Yes. Yeah, this suffers from fragmentation for sure. So it's a, yeah. And also it kind of is, so let's say I knew that my next neighbor was bigger than 1, but its neighbor wasn't. It'll actually go in and then go and find one that is of size, my size minus 1. So if I ask for a slot of size 3, it'll find one of size 2, but the value it returns won't be a consecutive value. So it doesn't, it can end up searching the rest of the heap. So in a degenerate case, I could end up for every one going and searching the entire heap, returning something, but it's not valid. So I did all this computation for nothing. It's a compromise. And this function's terrible, so I'll fix it. Yeah, so let's find space for. So let's go look at the mark. So the mark is, I believe, fairly simple. We pass in that get roots function. For some reason, it can be nothing or it can be a function. If it's nothing, I just get the root set. Otherwise, I call the function of the head of the get roots. So I pass in something. Because I don't fully get how var args work or optional arguments work in Racket, I make sure that if it's not an empty list, I know that there's a function in there, so I could grab that function out and call it. That gives me all the roots, but those aren't memory addresses yet. They are just these things called roots. So I have to map through all of those roots running this function that will, if it's a root, read the root, otherwise it'll return it. This is so I could test. So I can say, Mark, here's the addresses, here's the roots, go in and it'll just grab the roots. It'll just work with those memory addresses instead of having to do whatever I need to do to get it to work right. And then I just build up a list of white nodes, which is the disjoint. Anyway, it's like, yeah, it's the so I just build up the entire list and then remove all of the gray cells from it. And then I do my perform mark function, which takes, this is the blacks, these are the gray cells, and these are the white cells. So if the gray cells are empty, I know that I am done garbage collection. I just remove all of the black cells from the white ones, and those are all the memory that I have to clear. Otherwise, I check the item, grab its address, grab the addresses it uses, append its value to the list of black nodes, and then I append its children to the list of gray nodes, and then I just recursively call mark.
What's the distinguishing factor between the blacks, the whites, and the grays? Is it the whites you've never seen before?
Yeah.
The grays you saw last time, and the blacks you saw the time before?
So black nodes are ones that I know are live memory. Gray nodes are ones that I've found a reference to, but I haven't checked their children yet. And white nodes are, as far as I'm concerned, garbage, but I have to run through my entire heap to make sure that I remove all of those. Yeah. Yeah, that was the those were the they're the red rectangles. Anyway. And yeah, so this is my garbage collector. It works. It's not very good, but and let's just look at testing, because this was really, really helpful. So they provide this test thing that just you run a function and then you can verify when you get back. So I was able to, unfortunately you can't give it names, so I just used comments. So test finding available addresses for consoles. I added some like assertion stuff. It's weird. Let's see one that's interesting. Yeah, so this is kind of where things are a bit more interesting. So they give you the ability to test things. They let you test with example heaps, and they let you provide example roots. So you can say, I want you to run this test. Here's the heap you're going to use. So it's a vector containing these values, and this is your root. So the root is at address 4. So 0, 1, 2, 3, 4. Do your mark. So if we were to go through, this is a const cell, so it contains 2 references. Those references are at address 0 and at address 2. And then we run the mark, and we see that these 3 aren't being referenced anywhere, and they will be returned as the list of things that need to get collected by our garbage collector. Yeah, this was me. This is my first test, I think. Yeah, so this is just the testing. So I did write a lot of tests just to help me make sense of things. And it's nice because whenever you come up with like new examples, it's really easy to just build out those test cases and go in and get feedback on it right away. Yeah, I started by just putting them in my garbage collector class, and it kind of got out of control. So I learned how racket modules work, so I could go in and like run these without having to run it whenever I go to run my actual programs. What's going on? So here I implemented Newton's method. So these are the derivatives. So the square of x, and then its derivative is the double of x. So this is what we're going to do to find what the square root of 612 is. I was reading through SICP. I could have just put in 1, but I found this on Wikipedia, so I rolled with that. So what we're going to do is we are going to, okay, hold on. So we're going to I hate macOS. I hate it so much. I'm so confused. Okay, I'm just gonna quit Dr. Racket, and we're just gonna start it up again. What was the problem? I don't know what
Too many desktops.
too many desktops? Okay. Okay, so I'm just gonna open up my collector, and I'm gonna open up that Newton's method. So here's my collector. Here is Newton's method. So it's just an iterative method. It goes through until the iterations are 0 and it returns the guess. And this is my garbage collector. So I'm gonna run it with the debugger. It's gonna ask me some questions. I'm gonna say yes, so that I will step into this file because I end up using it. And all right, so as you can see, the heap visualizer is getting ready. Just gonna put a breakpoint here. So we're gonna end up with two things on our heap after this, like by the time we get to this breakpoint. So let's just go. All right, so let's go to that heap visualizer. So we have two flat values on there. Those are the oh no, we have three. So that's the Newton's method. That's the function I defined, the square function and the double function, and the rest of this is all of my free memory. So let's step in. All right, so we are trying to allocate a flat value. I don't know if I can. So it's a value of 10. So everything gets allocated onto the heap. So we're gonna go. Let's just. Okay. Step out. Then if we look, we can see that the primary value of 10 has been added. Now that's all cool and stuff, but let's go to the fun things. So let's actually go to the mark and sweep phase. So this does cause my garbage. So I will end up building up enough garbage that I have to clean it up. All right, so we have gotten to the point where our heap is full. As we can see, there's a bunch of stuff. So there's all these references going on, pointing to things. These are like, whenever we run a test, that result gets stored on the heap. So all of if we look at my Newton's method, every one of these evaluations gets stored on the heap. So it's really easy to build up garbage really, really quickly. And so now we have to go and figure out what is alive and what is not. So right now the list of black nodes is gray. We know that all of these addresses are references from our roots, and this is all the addresses that weren't referenced. So they could contain actual values. And then we go through and we just iterate through them. So I'm just gonna do this, pause at this point. So actually, yeah, we'll go with that. All right, so we have these new grays that are it's the appending of grays. So we can see that the address 5 was added. So 4 references to 5, so it's most likely a flat value. Yeah, it is, because we have 4 and 5 are the addresses. And then we will append. So now we know that our blacks contain one item, which is the address 4. And we will continue doing this until we get to the case that we've run out of gray nodes. That will be here. No, move that breakpoint. So if we look at our heap, or we look at our variables that are alive. There's a lot of duplication in here. Yeah, 1 and stuff like that. But we're gonna do the disjoint on it, so any duplicates don't really matter, and that will return all of those values to the sweep function. So let's just step in. So our addresses are all of these, So if we step out, just need to see where I am. If we step out, we should end up with our heap being freed. All right, so if we look at our heap visualize, and as we can see, a bunch of stuff was garbage, and we went through and ran and marked it all as free. So that is a example, like a simple example. I'm not doing any console stuff, which is unfortunate, but that's us going through, finding all of our references, and anything that isn't referenced, cleaning it up. And as you can see, there was a lot of garbage that I ended up creating in this function, or in this call. Oh, and I had to garbage collect again, so let's just let it run. And then when it finishes, we get a result. It's at location 60, and we were able to compute what the square root of 612 is. Yeah. So that is just an example, and this is our heap at the end of everything being run. The visualizer gets kind of gross at some points, but it was really handy just figuring everything out. And if you're looking to play with building a garbage collector, I'd say this is something to consider looking into. Yes.
So you pointed out how kind of before the functions started running, you had the functions themselves on the heap, and it looked like they were just taking up one slot each. So I take it that this is this system just uses a simplified kind of abstracted model where consoles are the only composite values and everything else just takes up one slot.
Yeah. The comment was that it's like a simplified heap, and the only real composite values are consoles, as James mentioned. Even values like functions are just flat values that are pushed onto the heap. And also it's a value that doesn't go away. So if I was to build a generational garbage collector, I could go in and be like, oh, this has been here for a few collections. I'm just going to move this over into Gen 1. And then whenever I run the mark again, I don't even have to look at that. Yeah, so as Nate mentioned, this garbage collector is pretty terrible. It can suffer from some pretty there can be some cases where I end up with a lot of fragmented memory. So if you were to implement a garbage collector, you'd be like, oh, this is really not good. So you could implement a copying garbage collector that every time you run, all the stuff that's still alive, you move over. And they provide that functionality. You can reset the value. You can reset where a root points to, or you can reset where a value points to. What else? I have some other notes here. Yeah, you can implement a compacting garbage collector. You could do a bunch of things. The GC, the GC world is your oyster. You can go in and you could grab. You can grab a book and read on how to implement any garbage collector. Go in here and do it. It's going to be a lot simpler. You do have a lot of constraints going on. I was going to try to do a bit mask market sweep garbage collector, but working with bytes, I'm not very good with working with bytes in Racket yet, so that was kind of awkward. Another thing that is going on is the CompSci Cabal is going to be covering garbage collectors for the month of February, so it's the month of garbage collection. So if you're interested in learning more about garbage collectors and the various schemes that there are, we'll be covering one paper, or we're going to be covering one paper in 2 parts, and then we're going to be covering the unified theory of garbage collection, right? Yeah, so the other one is uniprocessor garbage collection techniques, and then the other one is the unified theory of garbage collection. And at the end of that, we will be showing off garbage collectors or explaining garbage collectors that we've built. So if you want to do that and you want to build a garbage collector and not get completely bogged down in C or something, maybe consider taking a look at this. It's a little bit weird, and if you're new to Racket, or it can be super overwhelming. And at first, whenever I first got into it, I was really overwhelmed. But there's some good examples online you can look at, and they'll kind of help reveal some light on what's going on and all of this stuff. So if you're interested in continuing with garbage collection, there's that paper I mentioned, which Leo will be covering on Friday, the first 2 parts. And there's the garbage collection handbook. There's another one called Garbage Collection. Michael Bernstein went super hardcore into it. He's written a bunch of blog posts about it, and he did a talk about garbage collection at Goruko back in 2013. And it's a really good talk. Well, a lot of his talks are really good, and this one's really good because if you're into Ruby and you kind of want a really high-level understanding of it, he goes through and covers various things and the history of garbage collection and all of that. So it's a really, really good talk, and I highly suggest you take a look at it. So that is the end of what I have to say. And if you just have any questions or comments, feel free to ask. Otherwise, these are my details. And yeah.
I was actually just wondering, so you showed us an example of a tracer that you built. Does this same module give you facilities for testing out reference counters, or is it just tracers?
I don't know. I haven't looked into that. You might be able to. You could possibly do something. I haven't read up on tracing or on reference counters, so I wouldn't know how to implement one. You could probably, using some kind of metadata like what I did here, store the reference counts, and then whenever that reaches 0, you just clean it up right away. So you'd always do something like that, but I don't know if you will know when something is no longer referenced to. So you might not be able to do it with.
Yeah, the reason I asked was because the API you showed seemed to be really tracer centric. You've got your triggering collection now, as it were.
Yeah. So I don't know if you can do that. It'd be really cool if you could.
Yep. Something to look into for.
Yeah. So the question was, can you implement reference counting garbage collectors? And the answer is I do not know. Yes.
So in the API you showed me one of the earlier slides. There was a hook for set card and set trigger, right? That was hooks that your GC implementation get, right? Set first and set last.
Yes.
Set rest. Presumably you could do your ref counting in there and trigger your free.
That's true. Yeah, you might be able to do that. So I made it to that point. So yeah, you might be able to. I'm not too sure, but that'd be something to look into. Yeah. So I just implemented a very simple tracing garbage collector. But they say that they've had They mentioned in the paper that they had students implement all different kinds of garbage collectors. So you might be able to implement a reference counting garbage collector. But yeah, so. Any other? Oh, you had a question. Yes.
So actually, on that same slide,
I'm just gonna stay there.
Yeah.
Yeah.
It struck me as interesting that the deref call is something that the garbage collector would provide. Because I guess I was thinking that that just seems like such a basic thing to deref a pointer. But I suppose so that seems to implicate that if you were doing a fancier garbage collector, then you would have potentially more exotic implementations of deref. Is that right? Like that you would like you mentioned a compressing garbage collector or something like where so would it be that you would have like some level of indirection where you're saying like, oh well, you have this pointer, but it's actually like I'm compressing stuff, so it's actually stored over here instead of where you think it is, or something like that.
It could be, yeah. I'm not super sure. My stuff was really simple. I think you could. I was thinking of really cheesy optimizations I could pull off. Like every time I create a const cell, I have an empty cell at the end, so I could pull something where the empty cell is it's always alive, like it's a singleton, like the way nil is or something like that. So I could probably do something along those lines where it's just certain things, or if I realize something's getting allocated a lot, I can maybe put it somewhere.
Right.
And I store its address, and then the deref would be a deref of a deref, like it would be a deref of a deref.
Yeah.
I don't know.
So the garbage collector could have its own, it manages memory however it wants.
Yeah, 'cause-
and it, whatever kind of, like, optimizations it wants to make, like, it can.
Yeah, because
Kind of
this is
that-
the only way that we're getting into it, right? We're not
Yeah.
actually we're saying, oh, something's stored at address 8. What is that? And then
So-
the garbage collector could do some crazy stuff, and it was like, oh, it's actually 12.
It's interesting because, like, now this really makes me think of garbage collectors as being like a heap manager. It's not just garbage collection. It's also like your whole interface to the heap is
Yeah.
through the
Yeah,
garbage.
it was really enlightening getting to do this. I had a real fun time. There's a lot of like confusion and stuff like that, and figuring out what's broken. But it was really, I had a real fun time building a garbage collector. It's great, and everyone should build a garbage collector. Are there any other questions?